Bismillahirrahmanirrahim. Assalamu alaikum ji. Welcome back to machine learning. We were talking about the concept of dimensionality reduction. In the previous video, I talked about feature selection based dimensionality reduction. In this video, we will talk about feature extraction based reduction in dimensionality. We will start with feature extraction in general. How do we achieve feature extraction based reduction? And then we will converge towards, we'll move towards one of the technique, principal component analysis, PCA, to carry out this feature extraction based reduction. Okay, let's talk about feature extraction in general. So we defined this notation in the previous video, that we have d number of input features, and using a mapping function f of x, we want to obtain a new set of features z1, z2, k. So given d features, existing features, through a mapping f of x, we want to obtain k number of new features, right? So this mapping function can be linear, or it can be non-linear. It does not need to be linear. If you want to interpret this mapping, so this is a projection of the data in d-dimensional space, in a higher dimensional space, to the lower dimensional space, or a k-dimensional space, right? This is a mapping. This is a projection from this d-dimensional space to this k-dimensional space. Okay, mathematically, we want to find this mapping f of x, and this mapping is optimum in a sense that it preserves the desired information. It preserves the information content. It minimizes the approximation loss. It minimizes the reduction in the accuracy as much as possible. So when you move from d-dimensional space, say 784, to a k-dimensional space, say 10, right? So obviously you expect to lose information, right? So because this is a very, very high dimensional space, right? So you expect a loss of information, but this mapping should be defined in a way that you preserve most of the information, or you preserve the desired amount of information in this mapping, right? Or you minimize the loss in information from moving this higher dimensional space to this lower dimensional space, right? Okay. Okay, as I just explained, finding optimum mapping is equivalent to optimizing an objective function. This objective function could be loss in information, or this could be loss in accuracy, or it could be approximation loss, and so on and so forth, right? So we can define different objective functions to quantify this information loss from one space to another space. Okay. We use different objective functions in different methods. We minimize information loss. So mapping, okay, when you talk about methods in which we minimize information loss, so these methods represent the data as accurately as possible in the lower dimensional space. That means we have representation of data in this space, and we have a representation of data in this higher dimensional space, right? And when you take a difference between these two, right, when you compute the error between these two representation, so when we minimize information loss, in fact, we are minimizing the difference, or some objective function that quantifies the difference between these two data representations. Okay. Another group of methods maximize the discriminatory information. That means so these methods these methods maximize the ability to discriminate in the lower dimensional space. An example is linear discriminant analysis. Okay, let me explain, let me summarize the difference. In minimize information loss, right, we do not take into account the class boundaries, right? So we treat the data points that correspond to different classes, we treat them same in a same way, right? But when we use maximize discriminate information, we use the labels that are associated with, or use the output values for the input values in carrying out the dimensionality reduction, right? And we reduce the dimensionality from the higher space to the lower space such that the discriminatory information, or these are separated in a way that you can have an efficient classifier. Okay, so here we only focus on principal component analysis that minimizes the information loss, or that minimizes the approximation error, or the error between signal representations in the higher dimensional space, in the original space, and in the lower dimensional space. Okay, so PCA is linear mapping, and we love linear mappings because they are simpler to compute, and we can have a very good mathematically analytical representation of these mappings. We can carry out analysis of these linear mappings. Okay, let's talk about principal component analysis. I will first talk about the geometric interpretation of this principal component analysis, and then we will we will mathematically formulate the steps which we take to reduce the dimensionality using PCA. And finally, I will conclude with the help of one example to illustrate this mathematical formulation. Okay. We very briefly formulate that given features in d-dimensional space, we want to project into a lower dimensional space using the following linear transformation, right? So this is a linear transformation, right? So if this x belongs to R D and this z belongs to, so let me write here, so z vector belongs to RK. What about W? W is a matrix, right? And you are multiplying X with W transpose. So in fact, the transformation is defined by W transpose. Right? Can you tell me the size of matrix W for the following cases? So we want to find best planar approximation to 4D data. What is the size of W? So Z belongs to RK, X belongs to RK, X belongs to RD. What about W? So W should be size of your data, D, which is in this case 4, right? So W belongs to R 4 cross 2, and W transpose would be R would belongs to R2 cross 4, right? Similarly, we want to have planar approximation to 100D data, right? Now W belongs to R100 cross 2, because what you want is a planar approximation, a 2D approximation of 100 dimensional data. Right? In general, the size of W would be, what do you expect? R D, dimensions of inputs, n times k output, right? And W transpose would be in RK cross D. Okay, so how do you find W? So we have this mapping, right? As we said earlier, that we want to minimize information loss. PCA indeed minimizes information loss. but PCA does something much better than, in fact, more than that. It minimizes loss, but it also achieves some very, very nice objectives. So we want to find this mapping while preserving as much information as possible and ensuring these two objectives. The first one is the features after mapping are uncorrelated, or it simply means they cannot be reduced further, right? So there is zero correlation between the new features, right? This is something very, very nice, right? So you want the features that are not sharing any information. They are uncorrelated. And second, the features after mapping have large variance. It simply means you are capturing the large variations in the data. If your feature have large variance, that means you are capturing most of the variation across your data set, right? So PCA is the one that achieves these two objectives by design, right? So we design principal component analysis. We'll design this technique in such a way that will serve these two objectives. Okay. Okay. Before I formulate PCA based reduction, let's talk about geometrical interpretation of PCA. Or we build a geometric intuition of PCA. Okay, I give you this data. So data is in R2, and we have a binary classification problem. So blue data points belong to class 0 and red data points belong to class 1, right? So we have this data set available with us in R2. What is D here? Let's say D is equal to 2. And say we want to carry out a reduction in dimensionality, and we want K is equal to 1, for example, right? Okay, what is PCA doing, right? So PCA generates two directions. So data is in R2. So, and these are the natural bases. So x-axis, we have y-axis. Each data point has two components: projection on x-axis, projection on y-axis, and usually we use x1 and x2. This is x1 direction and this is x2. We do not use x and y. Instead, we use x1 and x2. Right? Okay. So these are the natural. These are the standard bases. Right? X1, x2 in a standard coordinate system. In PCA, when we carry out principal component analysis, so PCA gives us two vectors that are again orthogonal to each other, but they have orientation in a way that one of them carries the largest variation of the data, and the next one carries largest variation after the first component, right? So when you carry out principal component analysis, you are in R2, you will again get two orthogonal, two perpendicular components vectors. And when I carry out this PCA on this data, I get these two principal components, right? So I will call this one as the first principal component, and this is second principal component. And if you see, first principal component is along a direction, is aligned with the data, is oriented in a direction that has the maximum variations across data, right? Agree? Okay. Once I obtain these two principal components, if I represent data, originally data is represented in the form of x1 and x2. if I represent my data in these new bases, in the using these two vectors, right? Okay, let's see. Once we obtain principal components, so I have represented my data using principal component 1 and using principal component 2, right? If you see, this is principal component 1 and this is principal component 2. So what we had this, right? And what I obtained is this. This is simply a rotation of the data, right? Or orienting your data such that the data is aligned with respect to along principal components, right? So these are my principal component, right? This is the first principal component, this is the second principal component. Now the data is formed in terms of principal component 1 and principal component 2. Okay. And if you see, most of the data is along principal component 1. So I can ignore the second component, or I can ignore the second feature. If I ignore second feature and only keep the first feature, I will get this. So this is the representation of data along one dimension on real line, right? So k is equal to 1. Agree? So in carrying out PCA, we have not taken into account whether this data point belongs to class 0, this data point belongs to class 1, because we are not taking into account class boundaries, discriminatory information in PCA. We get all the data, we find these principal components, we represented data using these components, that is simply rotation. And once we have rotation, because most of the variations are along my principal component, I have dropped this one. Right? So I only kept this, my first principal component. So there are 3 steps which I've just explained in finding principal components. The first step is you find principal components, rotation, which we call change of coordinates, right? So we have standard coordinates, now we have a representation of data in using principal components. And once we have the representation in terms of principal components, we only keep the data along first. In this case, k is equal to 1. I've taken along only one direction, but if you extend this concept to higher dimensions, so you would say keep the data along first k principal components, drop the data that is along all of the remaining components. Okay, so I hope you could understand this geometrically, but as you progress, this all will make more sense. So by the time we conclude this video, you will have a very good understanding of PCA, inshallah. Okay, let's mathematically formulate PCA. And so we have n featured vectors of the form x belongs to x in Rd, right? So we have n data points, and each data point is in d-dimensional space. So d represents the number of features and n is the number of data points. Mathematically, we want to represent x in the new space, in this rotated space of lower dimensionality, using only k bases. Right? So these are the k bases. In fact, these will be our principal components. Right? Using only k bases. So this is the representation in these new bases. Right? If you see, I have chosen v1, v2, and vk. Right? So now I want to represent my signal as a linear combination of these k vectors. And the good thing about these k vectors is they are orthogonal, right? Orthogonal means so vi, vj, you take an inner product with these two, you get 1 when I is equal to j, or 0 otherwise, right? Or right, Kronecker delta ij, right? Okay, so we have represented data using only k number of vectors, and I call it x hat. So if we connect with what we said earlier, x hat is a signal representation in the lower dimensional space, right? Because in this lower dimensional space, what is size of this space? So I have represented x here as a linear combination of k number of orthogonal vectors. So dimensionality of this space is k. Dimensionality of this space is d, right? So x in this space, x hat in this space. The error, the difference between these two would be x minus x hat. That is error, right? In PCA, we minimize Euclidean norm of this error, right? So we find these V1, V2, Vk such that Euclidean norm of x minus x hat is minimized. You could choose other, but this is distance, right? You could choose some other measures, but in PCA, we minimize Euclidean norm of x minus x hat. Right? So as I said here, V1 to V2, Vt into Vk. So these vectors represent the k number of orthogonal vectors that form the basis of the subspace of dimensionality k. Okay, this is the problem formulation, right? So okay, let's talk about how do we find these basis vectors v1 to vk. Right? So I will talk about the steps which we carry out to find these principal components, and eventually to carry out dimensionality reduction. Okay, the first step is we compute sample mean. What do we mean by computational sample mean? So we take a mean along number of data points, right? So we have, if you see, I would define a sample mean, I call it x bar, right? And what is this? You take x1 plus x2 plus x3 and you sum all the features, and you take average value of all of these. This I call sample mean. So summation is over the number of feature vectors, right? From 1 to n. It's not along d, right? You're just summing all the data points you have, and you just divide by the number of data points. Okay, once you obtain this x bar sample mean, we subtract sample mean from the data, from each feature vector, right? So what is the size of x bar? X bar belongs to RD. Okay. So we subtract this x bar from every xi, right? And we call the resultant SI. Right? So SI is simply xi minus x bar. Right? We subtracted mean from every feature. So what's the interpretation of this? So the interpretation is that you have data points, say you're in R2, right? You have data points, subtracting mean, that you're shifting the center of the points to 0. Simply shifting your data to the origin, right? So now, when you take average value of SI, okay, if we ask you this, I is equal to 1 to n SI is a vector. Compute this. So this will be 0, right? Center mean. This is now because SIR, because you subtracted mean, so the mean is 0. Agree? Okay. Move towards next step. We have SI. The next step is we calculate the covariance matrix. Okay, let's talk about what do you mean by covariance matrix, right? Covariance matrix is very related to correlation between two vectors, but there's a slight difference in normalization. Okay, And in fact, I encourage you to find the difference between correlation and covariance. Right? Maybe spend 5 minutes and just find out what's the difference between covariance and correlation. Okay, coming back, we want to calculate the covariance matrix. So far, we started from X, we computed X bar, we subtracted X bar from every X, and we obtained SI, right? So zero mean data. So now we have these, right? So what is special about these vectors? There's zero mean because we subtracted mean. And we calculate the covariance matrix by simply using this mathematical formulation. Okay, how do you interpret this? Right? Okay, what is SI? What is the size of SI? SI belongs to RD. It's a column vector. That means R, to be very precise, RD cross 1. Right? When you multiply this with SI transpose, right? What about SI transpose? SI transpose belongs to R1 cross D. When you multiply these two, this is an outer product of two vectors, right? So what you get is SI into SI transpose, you get a vector that belongs to, so SI transpose, and this belongs to RD cross D. Simply outer product. You compute outer product of every SI with itself. And you keep on summing these matrices, right? When you take outer product, you get a matrix of size D cross D. And you keep summing all these matrices. My apologies. And you divide by 1. This is simply normalization, right? Average. Right? Okay. I will illustrate this with the help of one example very shortly. Right? So compactly, we can represent this covariance matrix sigma. So this is a covariance matrix. This is simply 1 over n S into S transpose, because I can represent this operation in this compact way. So because we're using, instead of using summation, I can write S into S transpose. With yeah. Okay. Okay, what is special about this covariance matrix? Okay, before we talk about something very special about this covariance matrix, how did you interpret the entries of the matrix? To make sense of this, I encourage you to use this definition of the covariance between two vectors, right? Okay, how do you define covariance? If I give you two vectors f and g, each belongs to Rn. Right? So we define the covariance of these two matrices as your first d mean. Right? So this is d meaning, right? So you subtract average from every value, right? So, and this is also d meaning, right? And what's left? It's simply inner product, right? A normalized inner product. Okay, and try to make sense of this one. So we have this covariance matrix, S into S transpose. And what is special about this covariance matrix? This covariance matrix is symmetric by definition because it is S into S transpose. Right? If you take a transpose of this matrix, what do you get? S into S transpose whole transpose, and you simply apply the matrix equality that A into B whole transpose equal to B transpose into A transpose. So in fact, what you get is S into S transpose again. So the covariance matrix is symmetric. And what is special thing about symmetric matrices? So for a symmetric matrix, the eigenvectors are always real. And the eigenvectors are always orthogonal and the eigenvalues are always real. You can also show that the covariance matrix is positive semi-definite. This is very easy to show. How do you show this? We need to recall what do we mean by positive semi-definite matrices. So we say a matrix, let me start with sigma. We say a matrix sigma is positive semi-definite if you multiply this sigma. Okay, what is the size of sigma? D cross D. So you take a vector, say you take any vector of size D, say call it, I use something which I have not used before. Maybe I take, say M transpose into M. Right? So when you multiply matrix with these two vectors, what do you get? A scalar value. If this is greater than or equal to 0 for every value of M, for every vector M, we say a matrix sigma is positive semi-definite. Okay, what's the interpretation? The interpretation is the concept of positive semi-definite is similar to a scaling a vector by a number, right? So sigma times M would be a vector, right? And you take inner part of that vector with M, you get something greater than or equal to 0. That means the angle between these two, sigma M and M transpose, is less than 90 degree. Sorry, yeah. So this is the maximum, right? So that means, sorry, it's between plus minus 90, right? So it can be this way or it can be this way, right? That means cosine is positive. Cosine of angle between these two. So positive semi-definite matrices do not change direction of the vector. When they act on a vector, they do not change direction of vector. This is similar to scaling by number. If you scale value by, if you scale a vector by say 3, a vector gets elongated. If you scale by -3, it also reverses direction. Right. So the same, this is an extension of the same concept for matrices. Okay. You don't need to know this, but this is something good to know. So size of sigma is D cross D, as talked earlier. This is something special about covariance matrix. Okay, so once we have this covariance matrix, that was step 3, right? So we started from X, we obtain S, using S, we obtain covariance matrix. And once we have the covariance matrix, we carry out eigenvalue decomposition of covariance matrix. For any matrix, for any symmetric matrix, we have this eigenvalue decomposition of the covariance matrix. Since covariance matrix is symmetric, eigenvectors would be contained in V, right? So a V would be matrix that contains D orthogonal eigenvectors, and each vector belongs to RD. Right? And we refer to this V1, V2, Vd as principal components. So these are those principal components which you want to find. Right? And this matrix D, so this centered matrix D is a diagonal matrix, and the values along the diagonal are lambda 1, lambda 2, and lambda D. So these are eigenvalues of the covariance matrix. Right? So due to the fact that this is positive semi-definite, eigenvalues would be greater than or equal to 0. And since this is symmetric, eigenvalues are real. Right? So we will have eigenvalues, say lambda 1, lambda 2 is greater than or equal to lambda 2. Usually we index in this way that lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda 3, and so on and so forth. Right? And finally, lambda d can be greater than or equal to 0. So these are the eigenvalues. Okay, so lambda 1 is an eigenvalue that is associated with the eigenvector v1. Lambda 2 is an eigenvalue that is associated with the eigenvector v2, and so on and so forth. Okay, so we have obtained principal components. So that is what we wanted, the first step, right, of all this reduction. We wanted principal components, and once we have principal components, we simply want to project data onto principal components, and you get Z. That's it. Right? If you recall, we needed K out of these D principal components. How do we select K out of these D? The answer is simple. We recall the objectives. We want to select the components along which we have the maximum variations. Right? And the variations are defined by the principal components are aligned, and the variation is explained by the eigenvalues. So we select the ones out of these D. We select the ones that has the K largest eigenvalues, that have the K largest eigenvalues. Right? So if we follow indexing of eigenvalues, that lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda 3. So we can construct our mapping matrix W in this way. W would be V1, V2, Vk. You select first K principal components corresponding to K largest eigenvalues. Right? And once we have this W, we can obtain, this is the W what we wanted. We get Z. So Z would be simply a linear transformation of X using W. So this reduction in dimensionality can be better understood. Say if you have a representation of this mapping in form system, right? So we have X that belongs to RD, and you have this Z that belongs to RK. And this is a system which we have that is defined by W transpose. You have Z is equal to W transpose X. So see, Z is a representation of X in K dimensional space. Right? I hope this all makes sense to you. I encourage you to review again and to watch again these couple of steps to have a better understanding of these concepts. I will explain all of this with the help of one illustration in a while. But before I start with example, let's talk about the reconstruction error, or the error between the representation of a signal, the representation of a data in D-dimensional space or lower dimensional space. In D-dimensional space, that is a higher dimensional space, and a K-dimensional space, which is a lower dimensional space. So here we have X, here we have Z. I want to compare these two, right? So this is X is in RD, Z is in RK. How can we compare these two? In fact, we can project back this to higher dimensional space to make a comparison. Right? Using Z, we can go back to RD and to obtain approximation of X as this. So X hat will be simply given by, this is how we defined it. Right? And if you use in matrix notation, you get W times Z. Right? And you can indeed show that this W or this choice of W minimizes the mean square error between X and X hat. Okay. Let's again connect with the objectives we had, right? So we had two objectives. The first objective was the features after mapping are uncorrelated. And second objective was the features after mapping have large variance. If you see all of our formulation, so we have served objective one because so the vectors in V or the vectors in W, they are orthogonal to each other, and orthogonality implies uncorrelatedness. So we cannot reduce further by using some correlation or some feature selection based method. So this feature representations, this is already uncorrelated, right? And objective two, in fact, we have used covariance matrix to define the mapping. And these principal components, so they are along the dimensions where we have most of the variation in the data by design. So we have served these two objectives by carrying out reduction in dimensionality. Okay, for a given problem, how do we choose K? Obviously, if you choose K is equal to D, no reduction in dimensionality. If you choose K less than D, you will lose information. And we want to choose K such that dimensionality is reduced and you do not lose much of the information. In fact, we can use the eigenvalues of the covariance matrix to quantify the amount of information loss. So using, we define a variable capital T to quantify the preservation of information in the mapping process, right? Okay, so on left hand side, I have defined a ratio. Right? In the numerator, so I have only used eigenvalues from 1 to K. In the denominator, I have used eigenvalues from 1 to D, all the eigenvalues. Right? Right? So this quantity represent in fact, this is quantifying the amount of information we have captured in the first K principal components. If K is equal to D, this factor would be 1, right? For example, if I take T is equal to 1, so I will have to choose K is equal to D because only K is equal to D ensures, in fact, this should be greater than or equal to be very precise. Only K is equal to D ensures that this is satisfied. And say if I want to preserve 80% of the information and I choose T is equal to 0.8. So using this equation, right, I can find K. So we can use this equation to find K. You start from K is equal to 1 and you keep on increasing K. And you will select the K for which this equation is satisfied or this inequality holds. And you stop at that point. Okay. Okay, now let's talk about one example. So in my example, I have taken D is equal to 2, N is equal to 10, and K is equal to 1. Right? That means we have a data in the two-dimensional space. I will take 10 data points in the two-dimensional space, and I will reduce the dimension by 1 to project data into one-dimensional space. Okay, the step 1 is we compute the sample mean. Let's first define data set. say we have this data set here, right? So we have 10 data points, and the each data point is in R2, X1, X2. It has two components, right? What's the first step? Sample mean. If I compute the mean along this dimension, right? This is, I get X1 bar. If I compute mean along this dimension, I get X2 bar, and this is given by X bar 1.81 and 1.91 as the mean. So what was second step? We subtract sample mean. So we obtain SI each new data point by subtracting mean from the existing data point, right? So you say you pick 2.5 and subtract 1.81, you pick 2.4 and subtract 1.91. Right? What you get is this data set S. Right? In this data set, I have 10 points. S1, S2, this would be S3, and so on and so forth. This would be S10, right? So next step, we calculate the covariance matrix. We define a set S by simply concatenating these vectors S1, S2, S10. So what is size of S? What is size of S1? 2 cross 1. And if you stack 10 vectors, size of S would be, so its size, that is, the size of this is 2 cross 10. And we define covariance matrix as S into S transpose 1 over n. What's the size of covariance matrix? 2 cross 2, right? 2 times 10 multiplied by 10 times 2, you get 2 cross 2 matrix. Okay. So for this data set, if I compute covariance matrix, I get this. In defining this covariance matrix, I have used 1 over n. In some textbooks or in some research papers, you may observe that they use n minus 1. This is not going to change the principal components. It will only slightly change the eigenvalues. So by default, if you use MATLAB built-in PCA, it uses n1 over n minus 1. Okay. So once we have this covariance matrix, what is the next step? We carry out eigenvalue decomposition of the covariance matrix. So we obtain V and G. So if for this matrix, if I compute V, I get this, and this is these are the eigenvalues. Right? How do you interpret these eigenvalues? Right? So 1.156, this eigenvalue is associated with this eigenvector, right? And 0.0442, so this is associated with this eigenvector. So I have two eigenvectors. And if you observe, these eigenvectors are orthonormal, in fact. You take equilibrium norm of each vector would be equal to 1, and when you take inner product of these two, get 0. You can check this, right? And once you have these eigenvalue decomposition, now we can construct W, because we need W for reduction in dimensionality. And how do you construct W? K is equal to 1. I have two eigenvectors. I would like to keep one eigenvector. Which one? The one with the largest eigenvalue, right? So in this case, if the first one is V2 and second one is V2, I will use V2 to construct W. And once I have W, I can use W transpose to obtain Z. So what is the size of W? 2 cross 1. W transpose 1 cross 2. What is X? 2 cross 1. So Z would be a scalar. In this case, that would be a scalar. Okay. So you get these data points. So this is the representation of your data that was in two-dimensional space in one-dimensional space using principal component analysis. And this is the representation along the dimension that has the most variations across the data in your two-dimensional space. Okay. So I hope this illustration has helped you in understanding the basic concepts. Okay, before we conclude, let's talk about some practical considerations and some of the limitations of PCA. In PCA, we assume that the data, we do not assume, but it's always good to normalize data before using PCA to bring the values to the same scale. And there are different normalization techniques being proposed in the literature, but the one that is very widely used, that is you subtract mean from each feature and you divide by the standard deviation of the feature. So this mean and standard deviation is computed along the number of points for each feature. So that's how you normalize each feature. Right. Okay, so and next, the covariance matrix of the reduced feature is projection along the components, and by design the features are uncorrelated, or in other words we can say that the PCA decorrelates the features. This is one of the strengths of PCA. Obviously there are some limitations. The limitations include that PCA does not consider the separation of data with respect to class label. I have said this earlier, that PCA does not take into account the label, the output that is associated with your input feature. So it only projects all the data irrespective of the class label to a lower dimensional space. Right? So in this mapping process, PCA does not preserve, or PCA may disturb the discriminatory information or the class boundaries we have in the data. Right? And the solution of this is linear discriminant analysis that takes into account the discriminatory information in your data set. It simply means that LDA must be taking into account the output level as well. Time permitting, we may review LDA in the later half of the course. But for now, so that's enough for dimensionality reduction. We know what do we mean by dimensionality reduction. We have also studied the feature selection based reduction in dimensionality, feature extraction based reduction in dimensionality, and for feature extraction as one special thing, principal component analysis to carry out this. We stop here and we will continue in the next module. Thank you, Chief.